Hi, welcome everyone. My name is Yuri Leskovets. I'm the chief scientist here at Pinterest. Thank you for coming to our speaker series. Sorry for the rain. We from Stanford are less used to it, but here in the city, I guess you are more used to it. So today I'm super excited to have my colleague from Stanford, Emma Brunskill, who's an assistant professor in computer science. She's a member of the AI Lab and the director of AI for Human Impact Lab. She came to Stanford from Carnegie Mellon, where she was an assistant professor before. Her research is around reinforcement learning for high-stakes decisions. So essentially the cases where mistakes or decisions you are making can have high consequences, which could be in education and similar domains. And her research won a number of different awards and prestigious grants. So help me welcome Emma, and let's hear her talk. Thank you.
Thanks, everyone, for coming out. Can everybody hear me in the back? Okay, great, awesome. So particularly in the rainy day, I'm from Seattle, so this is basically my entire life, but for some of you guys, this is a little bit different. Before we get started, I just want to highlight the people that are really doing this great work, which is my lab. In particular, Chris, with the arms folded at the top, was responsible for a lot of the technical stuff I'm going to talk about. So I just want to start out with sort of thinking about the number of decisions that we have to make all the time. So I was pretty shocked when I heard that, in fact, we don't even count a lot of or realize a lot of the decisions we make. Apparently, we make at least 200 mindless decisions about food every day that we don't even remember that we're making. We also are increasingly holding more jobs. So if you look at the Bureau of Labor Statistics, Americans on average held around 12 jobs over 30 years. Which means that we're changing jobs every 2 to 3 years, which means that we have to retrain, learn a new thing, maybe an entirely new work environment. And in addition, the pace of research output itself is doubling about every 9 years. So this is sort of the number of papers that scientific fields are putting out. And it's not that the total volume doubles every 2 years. It's just the sheer output of the number of papers is doubling every 9 years. And we're trying to keep up with all this stuff and make lots of decisions, learn new skills, make decisions about breakfast as well as our future life trajectories. And there's a lot of information. A lot of people are experiencing information overload. And so when I think about artificial intelligence, I think about computers helping us. So I would rather envision a future where computers are helping us deal with sort of these enormous number of decisions that we're trying to make in order to achieve our own goals and objectives, rather than thinking of computers replacing us. Now, when we think about this challenge of how do we teach computers to help us, it means that we really have to get at the heart of a lot of different things in artificial intelligence. In particular, these computers that we're going to try to teach to help us are going to have to think about uncertainty. They're going to have to think about what is the intention or objective of somebody, what can be done to help a person achieve that goal, and how can we do this if we're not even sure of the right way to help someone try to achieve this goal. Maybe the person wants to survive cancer. Do we know how to cure cancer? No. So what should a computer do to try to help someone survive cancer? Now, when I think of this from a formal perspective, I think of this in the lens of reinforcement learning, which is a sub-aspect of machine learning and artificial intelligence. So I think of there being an agent or a computer that is trying to take actions in the world to help a person and getting back some information about whether or not the actions or the decisions that agent is making is resulting in a benefit. So the agent can see, perhaps when they try something, an observation about how that changes the state of the world, and some sort of reward signal about whether or not it did something that was helpful. So if my robot drops the plate on the floor and it gets a stern look from its human it was trying to help, it probably realizes that that was the wrong choice. If a patient has really significant side effects, that was a bad decision. If the patient survives 5 years, that was a good decision. So it can get sort of indirect feedback about the decisions it's making to try to support people and try to use that information in order to make better decisions. So what I'm going to talk about today is some of the different work we're doing in my lab towards this vision of how do we teach computers to help us, focusing on counterfactual reasoning, intentional exploration, and moving towards fast, accountable reinforcement learning. Before I proceed, could I just get a show of hands of who here is already familiar with reinforcement learning, like you've taken a class with it or you've dabbled in it yourself? Has anybody here? Awesome. So a lot of people. Who here is not? There's a number of people that haven't as well. Great. Okay, so we'll try to give background. If I mention anything that is with terminology that doesn't make sense, feel free just to raise your hand, and also feel free to interrupt me with any questions. So I'm going to start with this issue of counterfactual reasoning, and I'm going to go back a few years now to when I started thinking about this problem. So this is the game Refraction. It's been played by about 500,000 students, well, 500,000 people online. It teaches kids about fractions by splitting laser beams and trying to feed spaceships so they can fly away. It was developed by my colleague Zoran Popovic up at University of Washington and his team. And when we were looking at this game, we were trying to think about how to use it to help kids and learners be engaged and learn things about fractions. So in particular, we were curious about this challenge of how do we do sort of adaptive personalized sequencing to support engagement and learning. So in general, when we think about sort of doing something like education or a game, there are often a lot of different options we could do for the player or for the learner. So you could imagine you doing sort of traditional types of problems, or doing games, or doing other different types of problems. And the question is, which one do you do when in order to maximize engagement and learning? And in general, the answer for this is going to depend on the student. So, depending on whether I'm doing well or poorly, and depending on whether I look engaged or not engaged, we might want to do different sequences of activities in order to help someone learn most effectively. Now, if you think about this sequence, it's probably apparent that if we have a number of interactions with a student and we have a really large pool of things that we could present to them, that the combinatorics of this start to grow pretty quickly. And so an alternative way of thinking about this problem is to think of a decision policy, which is essentially a mapping of a state of the environment, in this case, the state of the student, to a decision. So here a state could be something like, maybe on the last problem, the student took over 30 seconds and they got the problem wrong. So they spent, over 30 seconds trying to do the problem and they did it incorrectly. And maybe in that situation, we want to give them this next level. So a decision policy is just going to be a mapping from sort of the state of the environment, in this case, the state of the student, to what to do next. And in this case, we were really curious about, could we learn a decision policy from the existing data we had? We had about 11,000 students interactions with this game, and we wanted to figure out if we could use it to figure out how to make a good decision policy, which in this case was one that was going to try to maximize persistence. So how long does the student play before they leave? Now, this issue of sort of taking past data and using it to learn a better decision policy is an instance of off-policy reinforcement learning. It's also known as counterfactual reasoning. It comes up in a lot of different domains. For example, if you think about something like treatment effect estimation and optimization, if you want to figure out, which of these two different treatments to give somebody, that's an issue of that's a question of trying to do this counterfactual reasoning. If we think about sort of a decision policy, that's often going to involve making sequences of decisions. And it comes up in things like maintenance, how should we schedule different maintenance policies in order to help cars run for longer. It comes up in patient treatment ordering. It comes up in consumer decisions, and many, many other cases. So you might wonder why this is a hard problem. Well, the reason it's a hard problem is that it involves censored data. So the challenge is that you can't go back and see what it would have been like if you had not gone to this talk today. You only get to have one life, and so you get to only sort of observe the outcomes for the decisions you make. And that's going to be exactly the same for our agents and exactly the same in these sort of data sources. So it's censored because you can only observe the results of the decisions that are made and not the others. The other challenge is that it involves generalization. So as we think about these combinatorics, they grow very, very quickly with what I'll call the horizon of the problem, the number of decisions an agent will be making. And so in general, it's not going to be possible to think about all the possible different sequences of orderings we could do here. It'll grow combinatorially, and so we're going to need to have some way to generalize and say maybe you had treatment A and then treatment B, or treatment B and treatment A, but what might happen if you had treatment A, treatment A? Let's try to see if we can reason about that without actually trying it in the real world. So in this case, what we had access to is about this, 11,000 students' data, and we wanted to get a decision policy in order to maximize persistence. And so the first thing we did was we thought we should build a machine learning predictive model of the learner. So we can take in our data about how the students are playing this game and try to just build a simulator effectively so that we can simulate student play and use that in order to make a decision about what might be effective. So how could we maybe do that? Well, let's think about using the models as a simulator of the real world. So now we have our computer that's trying to learn to make decisions. It can select some form of teaching activity. And then you have a predictive statistical model of player behavior. You can see whether they get it right or wrong. You can have a simulator decide, how long that person played, whether they got disengaged, and then your agent can make another decision. Now, some of you in the audience have probably tried Atari before. Like, has anybody here done reinforcement learning with Atari games? Okay, one person in the back. So for others of you, if you ever want to take my class, so Atari is one of the big examples right now of success in reinforcement learning. Atari games is considered sort of an interesting test case because it's something that people take a while to learn how to do. And so now we can have reinforcement learning agents learn how to play Atari games. We do it as the second homework in my class, which is pretty fun. And so in that case, what are we doing? We are using, our agent is trying to learn to play Atari. And the nice thing about this is that Atari is a game. So you can do this loop as many times as you like. It just doesn't matter if it fails to play the game, 2 million times, and it does. Then eventually you can learn to take the right action. So that's one of the inspirations for this. Was like, well, we know if we have a simulator, like an Atari, then we can optimize for it. Now, can anybody suggest to me why this might fail? So why might this? So what we can do in this case is if we have this model as a simulator, we can optimize. We can try to figure out what would be a good teaching policy to get people playing for a long time. Right. So the suggestion was to say if we have any errors in our model, and people are notoriously hard to model, then they're going to get multiplied in this. Like every decision we make, we're going to get a little bit of error, and typically it's going to compound generally even worse than linearly, normally quadratically. So any errors we have in our model are going to amplify over that H-step horizon of us making decisions, which means that by the end, our agent can think, hey, I found the perfect way to teach students, and then when you deploy it, it completely fails. Because the model of the people that we have built based on our 11,000 player data is wrong. Okay, so as you might suspect, and as was nicely suggested, the model of the learner is bad. The policy you learned optimized to your bad model is wrong. Okay, so that's unfortunate. It's also perhaps somewhat expected. If we have bad models, then maybe we can't expect to be able to use them to make good decisions. Unfortunately, it can be even worse than that. One challenge that can come up is that even if you have sort of a best model in your set, it may not be the best model in terms of making good decisions. So I'm going to unpack that a little bit. So these are all really, really small models of the world. We're just pretending that we have a student and they're in one of 20 states or one of 5 states. So it's a very small set of states. In reality, we think learners are much more complicated, but imagine that we're just classifying people into being one of 20 states or one of 5 states of learning and engagement. So what do we see on the y-axis? On the y-axis, we see 2 things. We see log likelihood, and then I'll talk about reward in a second. Log likelihood here is being estimated on a held-out set, and that's going up. So it's saying we're getting higher log likelihood as we use more complicated models. Not much more complicated models, but a little bit more complicated models. And this is on a held-out set, so this is not overfitting. It really is better in terms of predicting player behavior to use a 20-state model. Here's the problem. If you use this model and then you compute the optimal policy for it, and then you see how good that policy actually is, that's the black line. And you can see here that if you take the policy derived by 20 states, it's much worse than if you took the policy based on 10 states. So this should be pretty concerning because it's saying, okay, well, maybe we think our model is pretty good, at least out of the models we've tried so far. But then when we optimize using that model, we're going to get a worse policy than if we'd used a simpler model, a model that looked like it was worse. So intuitively, why does this happen? It happens for a couple of reasons. One of the reasons is when we build these models, when we look at likelihood, we're often focusing on predictive accuracy. We're focusing on our ability to, say, predict how long the player is going to take before they enter in their next answer. But what we really care about is the features that are relevant for us to decide what actions are going to help them learn and what actions are going to lead to high reward, like the students becoming engaged and playing for a long time. And we often don't know what are those features in advance. We don't know which of the features of how a student is engaging with the game are the critical ones that we need to be able to predict accurately. And so when we generally just try to sort of uniformly accurately model a learner, this might be really hard to do with limited data, and we might be focusing on the wrong things. So again, just for some intuition on this, if you think of building a predictive model for an Atari game, that's like being able to predict pixels. And we're making progress on that, but it's still really hard. And you could imagine in an Atari game that there may be some features of the background which are not at all important to model. But what you really care about, say, is where the enemy is. Well, if your predictive model focuses on the background, because that's where most of your pixels are, it's going to sort of waste representational power. And it's going to end up making a model that looks good on your sort of predictive accuracy, but is bad when you make decisions. Okay. So in particular here, if you don't have sort of a rich enough class of models, you're going to get statistical bias in your model, and you may never get consistent estimates of how good an alternative decision policy, how good an alternative way of teaching students might be. So what's an alternative? An alternative is to not try to build models of player behavior and just trying to directly estimate how good a different way of teaching students might be, or how good a different way of playing Atari might be. And we call this offline reinforcement learning policy search using importance sampling. Importance sampling, as a refresher, is a nice technique from statistics which allows us to take data generated from one distribution and reshape it so it looks like the distribution we care about. So for example, imagine now that we're going to give a student more of level 1. We want to reshape our data so it looks like students are getting level 1 more and see whether or not that would help them learn better. So in this case, we can use this technique, and then we can use it to evaluate a whole bunch of different ways of trying to teach students and how to sort of sequence these levels to help them learn. It's not important to understand all of the things on the x-axis here, except for that we can do a lot of them. So we can think of sort of deep neural network, well, they weren't deep in this case, neural network-based policies. We can think of lots of different ways of trying to pick actions to help students learn. And then what we did is we estimated how good they were. So 0 here is random. Random is saying, like, we're just going to randomly select a level. And what you can see here is that we found one that we thought is going to be good. So over here, we've estimated a confidence interval over how good this new policy is. And we think this one is going to be significantly better than random. In fact, we think we're going to be able to increase persistence by 30%. So that's pretty encouraging. We'd love to be able to increase persistence by 30%. Let me just highlight here something that was unfortunate. So this was actually the expert policy. Not all of our data was collected as random. This was our expert policy that had been hand-designed by clever humans. Except for, unfortunately, we realized that it's actually worse than just randomly given levels. So this is slightly unfortunate and slightly embarrassing, but I think in a broader way, it's just exciting because it emphasizes why we need reinforcement learning in some of these complicated domains where we don't know what's going to be best. I think we often don't know what's going to be best, and if we could use computers and statistical machine learning to help us, that would be great. Now, I just want to emphasize again that this is predicted improvement. So this is using our old data set of 11,000 players and predicting how great it might be if we change the way that we teach students. So we'd like to verify this. We have sort of nice statistical guarantees that these should be asymptotically consistent. If we had infinite amounts of data, those estimates should be correct, but we don't have infinite amounts of data. We had 11,000 students. So what we did is we took some of those existing decision policies for how to teach students in different ways, and we ran a new experiment with 2,000 learners. And again, remember, what we're predicting here is that we're going to get a 30% improvement in persistence. And the cool thing is that we got a 32% improvement. So just like we had predicted, expert was worse than random. And it turned out that we could also sort of inform better ways that aren't personalized to sort of better static strategies. And importantly, our adaptive policy was significantly better than random, and it was 32% better. So I bring up this example for a couple of reasons. One is that we could use off-policy reinforcement learning to find a strategy for learners that really help people persist for much longer than before. 30% improvement is great. I mean, I'd love to have more, but I think that's a really great improvement. The other thing that I think is really cool about this is that we could predict this before we deployed it. So it's high stakes to deploy these things. This is impacting real learners. And we often want to be able to do this sort of thing of like trying to predict the future before we actually try things out to change the future. And the cool thing about this technique is that it could accurately predict that we would get an improvement and how big that improvement was, and that matched reality. Now, this particular technique worked because, unfortunately, students do not play this game for a really, really long time. So they tend to do on the order of 5 to 7 levels before they quit. It's an optional online game. In some other sorts of domains where you have a much longer interaction, it could be on the order of hundreds of steps, like in Atari games, or very long treatment plans. This type of technique that we showed here won't work very well. The estimates are too highly variable. So one idea we wondered about is, well, maybe we could kind of combine models, like that simulator I talked about before, with this sort of importance weights approach. And so then maybe if our model is good, we can rely on that, or else we can rely on these sort of importance weights. And this is known as the idea of being doubly robust, which is you're sort of both building a model of the world and you're trying to directly estimate the value of a policy. And these ideas come from statistics, and I thought they were really beautiful when I first learned about them a few years ago. The idea is that essentially it's an automatic way to be robust if either of these aspects happen to fail. They were brought over to sort of the reinforcement learning community about 8 years ago when people started thinking about these for multi-armed bandits, which is an instance of reinforcement learning where your actions don't affect your next state. So you can think of a series of customers. Whatever ad I show to a customer right now doesn't affect which customer comes in next. Question?
How do you do the confidence estimates of your predictions?
Great question. The question was, how do I do the confidence estimates of our predictions? It varies by the techniques. In the one there, I'd have to go back and look, but I'm pretty sure we did it probably by cross-validation in that case. In general, it's subtle.
Any good way to do it for neural networks?
Really interesting question. Okay, so the question was, can we do this well for neural networks? I'll talk a little bit later about neural networks. We have nice theoretical bounds for that. I think bootstrapping is a reasonable thing for deep neural networks. So people have used that for exploration, where they bootstrap it, and then they get a number of different estimates. Yeah?
How consistent are your estimates if your training data set isn't totally independent? Because right now, it sounds like you're just randomly assigned.
Yes. Great question. The question was, how good are our estimates if the training data is not IID? Basically, it's a series. I'll talk a little bit more about when we combine this with exploration style algorithms. Normally, in terms of the analysis there, then we want to rely on martingale type arguments to make sure that we can have valid confidence intervals. One of the really cool things that we've been finding recently, at least I think it's super interesting, Chris has been figuring this out, is that that by combining off policy with exploration, you can do better. You can have tighter confidence intervals. But they're not for the deep neural network case yet, so that would be nice. Okay, so these doubly robust estimates are nice, but some of the initial ways of kind of bringing them to reinforcement learning still made things be unbiased. And what we find is that in a lot of cases, you just want a really accurate estimate of how good a policy is before you deploy it. You just want really small mean squared error. I want to know whether or not, this new way of treating patients, exactly like how confident am I on that? Because later I'm going to be making decisions whether I should deploy this or not. So one insight that we had, this is with my former postdoc, Phil Thomas, is that we introduced a weighted doubly robust estimator and also something we call magic, which are still provably consistent, which means, as a refresher, if you have enough data, they will converge to the true estimate. But it turns out they often can have much better performance. So in particular, this is a tiny domain. This is just a small grid world, which for better or worse in reinforcement learning, we used to think about a lot. Now, fortunately, we think about bigger problems, but it's nice to illustrate. So what we have here is, this is essentially the amount of data. It's a log scale, and this is our mean squared error. And you can see our magic estimator that's in red is getting sort of an order of magnitude better mean squared error. than some of the other techniques. Now, you might look at this and you're like, okay, but this is, this is a small mean squared error, and that's just a little bit larger. That's a log plot. But I think the important thing to notice there is that that means you can need an order of magnitude less data to get a good estimate. So that's why this plot is important. Because if we can reach this with 2,000 data points instead of with 20,000, that's important. Because if we're going to run a clinical trial, we might only have, 100 patients. And we still want to be able to figure out what's good for those patients and other people with the same disease. So if we can need an order of magnitude less data to make good decisions, that would be great. Okay, so doubly robust type methods, they have a lot of potential. But one thing that we found there is that we're sort of using these other kind of important sampling techniques to get around the fact that the models might be bad, but empirically the model often looked really good. So we're like, okay, well something, this is sort of surprising. Like the model, probably it's biased. We don't, we want to be careful about it asymptotically, but with small amounts of data, the model was often really good. So I mentioned before that if we have statistical bias in our model, our concern is that even asymptotically, we're not going to get a good estimate of if we use that model to get a new policy, how good that policy would be. So what we were thinking about as we sort of revisited this issue more recently is that maybe the models aren't bad. Maybe we were just using way too simple models. This is, of course, something that many people have been thinking about over the last few years. So we were thinking, maybe we're using the wrong model class. We definitely don't think that people are 20 states, to capture all of human learning. And maybe not only were we using the wrong model class, but we were using the wrong loss function. We were training these models in a bad way. So our idea was to return to models. And we're going to still think about Markov models, which means that the current state is a sort of a sufficient statistic of all the history. So we're going to still sort of try to capture all of human behavior with a current single state, but we're going to use a really rich representation. And we're going to train it differently than the way we normally train supervised learning. So this was with joint with Finale Dashi's labs over at Harvard, and we've been thinking about healthcare applications. So we were really interested in sort of how do we think about getting in data about like a patient and a treatment and having rich, complex models of their dynamics and reward in order to predict their next state. And we wanted to be able to use deep neural networks to try to capture this. Because there'd been some really cool work recently from David Sontag's group at MIT illustrating that even with fairly small numbers of patients or individuals, like on the order of 800 to 1,000, so large, but this is not ImageNet, that you could use deep neural networks and start to get pretty powerful models for the one-step case. So we recently presented this work at NeurIPS, and the idea is we call it sort of representation balancing Markov decision processes in order to do this off-policy evaluation, to figure out how we should treat people or to estimate the value of a particular decision policy. And we wanted to sort of think about 4 different classes of problems. We wanted to be able to move beyond making single decisions to these cases where we're really making a sequence of decisions. So we wanted decision policies, not just single treatments. We wanted to be able to think about individual estimates. So often when we think about reinforcement learning, we think about, you play Atari 100 times, on average, how many times do we win? We wanted to think about cases where for different individuals, like babies versus elderly versus for every single individual, can we make guarantees on how good our estimates are? And I think this is important because one thing that I and many in the community, and probably many of you as well, are concerned about is fairness. And so we'd like to be able to understand, are we sort of trading off accuracy for one population in order to do better for another? And this allows us to help quantify that by getting what we often call individual treatment effects. We also wanted to be able to handle deterministic policies because we frequently have that. So I won't talk too much about the details there. We did this, and then the other main thing is that we used sort of some nice insights about fine-tuning, with the idea being that if a lot of your data doesn't match the new policy you want to evaluate, it may still be useful as a regularizer. So you can still use that to kind of generally fit your model and then fine-tune it on the data that does match your desired policy. We found that these types of estimators are much, much better than the previous ones in trying to be able to get good estimation. So just to sort of summarize this part about counterfactual sequential reasoning, I think the goal of this is to sort of be able to, mine old data to make the right decision for the right context at scale. But I think that there's tons of interesting questions here. We're definitely nowhere near done. So I think a lot of the work, including our own, has focused on evaluation, imagining that someone has a particular new policy in mind. But in reality, we often want to go to policy optimization. What should we do for a new patient? One big challenge is then a lot of real data. There are hidden confounders, which means, the treatment that someone is given may rely on features that are not in your data set. You might give smokers different treatments than non-smokers, and whether or not someone's a smoker may or may not be in their health records. So that's a really big challenge. Another thing is this fairness and accountability guarantees I was talking about. How do we make sure that we're making good decisions across the board? And how are we robust to this sort of misspecification? Question?
How many actions do you do in the medical system?
Great question. So the question is, how many actions do we take? So it depends. So you mean the sequence, or you mean the size of the space, or both? Yeah, so it depends. In some forms, it'll be on the order of 3 to 5. So in terms of the horizon, sometimes the number of decisions are pretty small. If you're thinking about like mobile health app, it's tons. It's daily, multiple ones a day. So Susan Murphy at Harvard often does mobile health interventions, and then it's a lot. But you may not be optimizing across that whole horizon. And then in terms of the space of treatments, I think that's another thing that's sort of different about our work compared to historically. Often there was just 2, treatment versus control. Of course, when real doctors are making their decisions or thinking about education, there's hundreds, hundreds of thousands. Yeah.
What's your action space here in the game?
In the game, I think we had on the order of 10 to 20 levels, so not enormous. But the number of state features was enormous because it's basically anywhere someone clicks. And so we had to figure out how to contextualize that. So the next thing that I want to talk about is intentional exploration. So everything I've talked about so far is this counterfactual reasoning problem. And I mentioned that we're doing some new exciting things and we're tackling the sequential aspect, but counterfactual reasoning is also something that a lot of epidemiologists think about, statisticians, econometrics, et cetera. So I think that RL can contribute some new exciting ideas there and bring it to a broader set of framing. But in machine learning, we're sort of concerned with some other really important questions as well. So I really like this summary of what machine learning is trying to do by Tom Mitchell. Tom Mitchell was the first person to create a machine learning department at CMU. In fact, I don't know, Yuri, if you graduated from there, if that was, but from CMU's machine learning department. But he wrote this really nice paper called The Discipline of Machine Learning. And he said, how can we build computer systems that automatically improve with experience, and what are the fundamental laws that govern all learning processes? And I think that's a lovely summarization of what machine learning is trying to do. But I haven't told you anything about this part yet, which is, I was talking about like someone's already collected this data, and now we're trying to use it to make better decisions. But we really, if we want like sort of true machine learning systems, true computers that are helping us, they need to get better with experience. And so they need to be able to reason about how to gather data in order to better help us over time. So we need to be able to move from like good reinforcement learning policies, decision policies, to good reinforcement learning algorithms that can actively gather data and do so in a way that allows them to make better decisions over time. So I'm going to call this intentional exploration, where our agent is thinking actively about what action should it take in the world so that it can quickly learn to make good decisions, ideally in terms of helping somebody else. Now, I'll just put a brief plug-in for theory. A number of my work focuses on theoretical guarantees. And the reason that I do that is that I think that theory allows us to have strong generalization. And what I mean by specifically is that we only can try out so many different empirical domains. And theory allows us to know that it will work no matter for any domain that we deploy things on. And I think that's a really lovely concept. The other is that theory can give us strong accountability in terms of how good it's going to be. So say not only will this algorithm work on any domain, but this is performance bounds on it. Before I deploy it, in this really high stakes situation, this is exactly what guarantees I can give to you. So I'm going to spend a little bit of time now talking about how do we sort of formally think about reinforcement learning. So let's think about running a reinforcement learning algorithm a number of times, and this is its return. So this is like the sum of rewards it got in a particular episode. So you could think of this in terms of the student example as this is student number 1, and this is how long they persisted before they left. And then maybe the reinforcement learning algorithm changes how it's teaching students. And for the second student, maybe it made some poor choices, and the student dropped out really early. On the third student, they dropped out even earlier, and then the system learned better policies for how to engage students, and they started to stay for longer and complete more levels. So this shows sort of the performance of a reinforcement learning algorithm over time, and we don't know what this is, but there's some optimal return. There's some sort of best possibility for your reinforcement learning algorithm, and I'm going to call that the optimal return. And again, here return is just the sum of rewards you could get in an episode, which in this case we can think of as teaching a particular student. So one way to quantify how good a reinforcement learning algorithm is by mathematical regret. So in mathematical regret, we think about how well the algorithm did compared to how well it could have done. And so we just subtract. So we're like, here, that blue bar shows exactly how remorseful our algorithm should be. And over time, hopefully it's getting smaller. And so when we think about regret, we just sum up all of that remorse. We just sum up all of those error bars, and we think about the rate of its growth. You want this to be sublinear. If it's linear, that's the equivalent to saying on every single episode you're making bad decisions and you're not getting better over time. So you want the rate of your regret to be sublinear, which means that over time you're hopefully making less bad decisions. So regret is a nice way to think about things, but in some cases it may not really capture everything we want about a reinforcement learning algorithm. So in particular, it may be okay if we're not perfect. We talk in reinforcement learning and AI about satisficing. So maybe it's okay if we didn't make the perfect decision. Maybe somebody persisted for 8 rounds instead of 8.5, and maybe that's okay. Or maybe our patient did well, but they still had a minor headache, and that's okay. So in this case, we think about what is sort of a bound from optimal that we think is okay for our algorithm to get to. And then we only consider things as mistakes if our performance is worse than that. So in this case, I've highlighted all the red bars where we think that our performance isn't tolerable. You can imagine for like a customer services organization, it might be if your wait time is over 5 minutes, that's not acceptable. You'd really like it to be 0, but above a threshold, it's bad. So in probably approximately correct reinforcement learning, which is related to probably approximately correct from supervised learning, we're just going to count up the number of bad mistakes. And we're going to bound how many there are in terms of the domain. So we just count up all of those red bars. Again, we never know what that optimal is, but we can bound in advance if that's going to be a lot or a small number. So these are different ways to sort of quantify how good a reinforcement learning algorithm will be in any domain. Okay, we can look at what its regret it will be in advance of us running it, or we can look at how many mistakes it's going to make in advance of us running it. And so the nice things about this is that they sort of guarantee that an algorithm is going to provably learn to make better decisions. It's going to satisfy one of the key aspects of machine learning, which is it's going to be getting better with more data, and it's going to be getting better at a sort of sufficient rate, or that we're going to bound the number of mistakes it makes, and that it will do so for any domain in the class, like any Markov decision process. Okay. And there's been quite a lot of work on this over the last decade or two. And in particular, one thing that I think is really nice is that recently, I think the tabular case, which is situations where you can actually write down the policy for every state individually. Can't normally do this. Most of the problems we want to solve are way more complicated, but it's good to start somewhere concrete. So for tabular MDPs, we can now have the same algorithm that has minimax results for regret and probably approximately correct. So just as a refresher, what does minimax mean? Minimax means that we have an upper bound on how fast regret might grow and a lower bound on how fast regret might grow, and we have an algorithm that shows that those are equal, basically. And same for PAC. So an upper bound on how many mistakes we might make, which is equal to the lower bound on how many mistakes we might make, and we have an algorithm that achieves that small number of mistakes. So we developed that recently. It's on archive. This is essentially kind of meaning the problem is closed, because that means that your upper bounds and lower bounds match. So that's nice, except for this is only for tabular settings, so we clearly have a lot of work to do still. I'll just say briefly about how these work for some people who may not have seen these type of bounds before, or these type of algorithms. They essentially involve careful optimism under uncertainty. So kind of love this because it means that we should all be optimistic, and tells us that math tells us that. So the idea is that when an agent is making a decision, it picks decisions that it thinks might be great. And the way it computes its uncertainty over those is based on its previous history of the actions it's tried and the outcomes it's seen. And essentially, it can compute an upper bound on the potential performance of any decision it might make by having upper confidence bound. And so it uses that to make decisions, and then it gets real data back about whether they're good or bad. And the intuition for why it's good to be optimistic is that either the world really is as lovely as you think it is, in which case, great, you're not going to have any regret, and you're not going to be making mistakes because the treatment really is fabulous. Or it's not as good as you think, and then you'll learn something. So if the treatment turns out to be bad, you'll learn something, you'll revise your estimates of how good that treatment is, and you won't take it as much in the future. And a huge amount of progress has been made over the last 10 years in terms of more careful optimism. So essentially, you want to be optimistic, but just enough. You don't want to be too optimistic, otherwise you'll try bad actions way too much. And so a lot of the recent progress has been in trying to make more careful, optimistic bounds. Now, when we look at these types of bounds, including the sort of minimax bounds, the way we often construct these lower bounds is we think about pathological MDPs, which are really, really hard to learn to make good decisions in. And so fortunately, in real-world problems, it's often much easier to figure out how to make good decisions, and which means that empirically we often see that many reinforcement learning algorithms can learn way faster than these bounds would predict. So one thing that we've been doing in my group recently is thinking about how do we have problem-dependent bounds. So how do we have algorithms that if the domain is easy, they need much less data to learn to make good decisions. One question that sort of came up recently, just as a brief aside related to this, is sort of this issue of like, how do you even specify which problem you're thinking about? So are we doing a reinforcement learning problem where we really need to really think about the sequence of actions we're taking in order to help, say, a patient be well? Or can we treat it as a bandit where basically we can make a single decision and we don't have to think about the impact of that decision on the future? And in many cases, it's not quite clear. Like if you think of going on to Amazon and you're making a product recommendation, do you have to think about whether the customer is going to come back tomorrow or whether they're going to go, on vacation at Christmas when you're trying to figure out what product to show them right now? Or can you just think, given the state they're in right now, let's just show them a product, and I don't have to think about how that's going to affect that customer in the future. So it's often really not clear whether we want to be a bandit or a reinforcement learning agent. And one of the works that we published recently at ICML, which is a machine learning conference, is that, at least this is again from the theory, so this is the sort of first baby steps towards this, but that you don't need to know this. That you can, if the problem really is a bandit, but you're treating it as a reinforcement learning problem, you can do provably as well as if someone told you it was a bandit. So again, this is the type of thing we want to work towards. If we want to democratize AI, we want to have algorithms that if the problem is easier than what you might think, then the algorithm should just adapt to that structure. You shouldn't always have to put it in advance, and that should reduce the burden of people who are using these algorithms. Another thing that we can do in terms of trying to get away from the sort of size of the bounds that we would get from the theory is to think about sort of satisficing with things like partial personalization. So this is a project that we worked on with Yahoo. We were thinking about making news article recommendations. And we were thinking about the fact that in the cold start problem, it's often really hard. Either you can treat everybody as identical, but then that might mean that me and Yuri might have different news that we want to look at, and so then we're both going to get sort of a suboptimal solution. Or because it's a cold start problem, you could just learn from scratch for me and for Yuri, and then we're just going to get bad recommendations for a long time. So We call this partial personalization. This is where we assume there's sort of some latent feature. There's sort of a number of different subclusters of people, and you try to quickly identify which cluster people are in. And so we found by doing this, this is the blue line, that we could quickly learn to get higher click-through rates than what we could if we were making either assume everybody, start from scratch for everybody, or assume everybody is the same and build on all the data. The other thing I like about this is that Yahoo would not let us run this on their on their system to start with, and so the way we evaluated this was all using off-policy evaluation. Was there a question? How many candidates? Good question. So in this case, this was news article recommendations. I don't remember the size of the article space, but in general, it would be any news article that Yahoo could be showing. So in this case, where you have a parameterized action space. You represent the articles by a set of features.
It might be, so their data sets have like 50 articles or something like that. Some Yahoo data sets.
I don't remember for this one. I don't think it's the same as the one that they released online, but I would have to go back and check. It's been a couple years. Yeah.
So for Thompson sampling, what algorithm, like optimization, sorry, not optimization, what model did you use?
What model did we use for Thompson sampling? Again, I would have to double check in the paper. I think in this case we're not doing clustering, so we're using like a single Thompson sampling modeling across everybody. Whereas here we're using explicit knowledge that there's, say, 3 different clusters.
Is it like a linear model or like context-free Thompson sampling?
I would have to check. I'm pretty sure it would have been, the question was what type of Thompson sampling model were we using. I would be pretty sure that it would be a linear model with uncertainty, probably Gaussian, but I'd have to double check. Okay, so the thing that I want to end with is to think about how are we going to start to move towards fast, accountable reinforcement learning. And this is the area where we're sort of starting to combine these insights between the work that we're doing in the off-policy sort of counterfactual reasoning with the trying to do fast, strategic reinforcement learning. So we're again going to be thinking about an agent that's getting to make decisions online, but where they want to be really fast. And the motivation for this comes from this following scenario. So the existing formalisms we have right now would do something like the following. So let's imagine that a father's coming in with their son to kindergarten, and the teacher says, we have this great new state-of-the-art AI system that is going to optimize your child's education. And the father quite reasonably asks, okay, well, that's great. How good is the system? And the guarantees that we have right now would say something like, it will only at most fail to teach 10,000 students how to read. But the rest of them will learn to read faster and better than any previous method. This is kind of what PAC would do. It would say on all but 10,000 students, we're going to make really good decisions. So can anybody guess what the father might say in response to this? Particularly if they're being somewhat myopic or selfish. What's that?
It's a more realistic approach than being optimistic. So giving both scenarios, because especially when we were kids, our parents used to take places or ask us to take advice from people who are only successful. Nobody went to those who were not so successful, right? So I would say this is a very good example of considering two factors. What if?
That's true. So they might feel like, well, you're probably being more realistic than perhaps some of us. But I think at least a number of people would probably have the reaction, particularly if they were being myopic, of, okay, is that going to happen to me? So think about this for patient treatments. If this is a patient treatment that is going to definitely cure cancer better with less side effects than anything that's ever happened before, except for 10,000 people are going to die, then naturally your question would be like, that's great for humanity, but I'd like to know whether it's going to kill me. So we would like to be able to have guarantees about how our algorithms are working on a per episode basis. And so we would really like to be able to sort of move beyond this into something more like, okay, for students like your son, the AI tutoring system would have an average that's at most epsilon k worse. Okay, you probably wouldn't say exactly that, but you'd say an AI tutor will have an average, a solution that's really close to optimal under the current strategy. So be able to sort of give some sort of guarantees of how good is the solution going to be for this particular boy, for this particular instance. So more generally, what we would like to be able to do is, if we think back to these sort of formalisms for evaluating reinforcement learning, we would like, before an episode, that the algorithm to output a certificate. So before it makes a decision for a customer, before we give recommendations to a doctor, before we teach a student, we would like to put a certificate, which is basically a confidence bounds on performance. We want to say, we don't know how good this algorithm is going to be for this particular person, but this is our bound on it. It's going to be somewhere between like 5 and 10, or this is, how uncertain we are on what the performance is going to be. And we have to do this before we get to see the actual outcome. And that means that people can intervene, because if they are not willing to tolerate the amount of uncertainty, then they can say, okay, I'm not willing to take that. Maybe it's too uncertain for me. Or maybe they are willing to. Or you can imagine cases where you provide people a bonus. You're a chef in a new restaurant, you're making a new dish, you're not sure if it's going to be good or bad. You see from your algorithm that you're really not sure whether it's going to be good or bad, and so you give it to people for free. So you can imagine doing all sorts of things if that information is revealed. But we want to both not just do this, and so this is essentially like an off-policy evaluation problem, like the things I talked about in the first half. But we also want the algorithm itself to be quickly learning a good policy. So of course we could just have a really bad algorithm and just have really wide confidence bounds forever, but that's not what we want. We want an algorithm that's also learning quickly. So this is led with Christoph Dan and with my colleagues Li-Hung Li and Wei Wei at Google. And so we recently introduced something we're calling policy certificates, which allows us to do both of these things. And one of the things that I like about it is that we're trying to move towards the deep neural network setting. And in terms of our theory, we do extend it to sort of contextual Markov decision processes, where the idea is that whenever an episode starts, you can imagine a patient or a customer coming in, you get background information in terms of a vector, and that determines your dynamics and your reward model. In some way that's unknown to you, but you get sort of some rich context. And I think this sort of framework is helping us move towards the really complicated settings where we would really like to be able to provide these types of guarantees. Now, one thing that I think was really surprising to me when we did this is that we found that we actually got benefits from trying to directly learn quickly and to estimate the performances we learn. So it ended up that sort of doing strategic exploration was helping us do better offline policy estimation, and trying to provide these certificates was allowing us to do better exploration. And I'll just give like a brief intuition for this. The idea is that now we explicitly maintain upper and lower bounds on the potential performance, and we can use that to guide exploration. And similarly, the fact that we are always trying to act optimally or optimistically can be used to get better confidence bounds on the policy that we're deploying. So that's kind of the high-level intuition for that, for why that ends up working. All right, so I think it's a really exciting time for reinforcement learning. I just want to highlight that we're very early in this journey, I think, still, and there's still lots of important questions about how to make things personalized, fair, and effective. And there's particularly a lot of work to be done of like how do we scale up some of the insights from the theory into practical algorithms that we can deploy. So I'd love to hear of any work that anybody else is doing on this, and thank you for your attention.
Great. So we have a time for a couple of questions, and then we can move to the room back here where there is food and drinks, and you can talk more to the speaker. But we can take a few questions now. Go ahead.
The question was about sort of the contextualization of decisions, and also, you can tell me if I'm summarizing it, the contextualization decisions and how could you put weight on good or bad decisions, and that it might be due to the context. I think that in many cases it is. We sort of want to have the right intervention at the right time for the right context. And so I think when we weigh whether or not something was a bad outcome, we need to be specific to that particular context, and we don't want to overgeneralize to say, well, maybe the outcome would have been totally different. You can imagine for self-driving cars, the conditions are completely different whether it's raining or not. And so you don't want to generalize, overgeneralize in that case. And I think one big challenge is how do you effectively use data without overgeneralizing? You can also put time in as a feature, absolutely. Yeah, time can definitely also be a super important feature.
So I think that what I took away from the slide on certificates is that certificates are a hard upper and lower bound. So the algorithm is guaranteed never to produce something that is outside of this range, and which I assume is true. If that is true, do you see any value in having a bound that is probabilistically, like an algorithm is probabilistically likely to be within the bound, but is allowed to drift above and below?
So these are all high probability bounds in most cases, so they're not guaranteed. They're guaranteed with high probability, and we have that high probability with respect to if it's a stochastic process, there's some probability they'll be outside. One of the things that we're doing that I didn't talk about now is thinking about safety and thinking about robustness. And so this is giving us guarantees and expectation. So just to be clear, like for that little boy we were saying, or that hypothetical little boy, we were saying, on average for someone like you, this is how good the reading program will be. But of course, that individual boy will only be taught to read once, or your patient is only going to experience chemo, this particular chemo treatment in the current status once. And so I think in many cases we want to think about the full distribution of outcomes instead of just expectation.
Thank you very much for the talk. I have a question regarding the policy explainability. So you mentioned the certificate. Do you think it's more the algorithm knows why the policy is good, or is the other direction, which is it's kind of prediction, like the log likelihood? Okay, this is what I predict. I don't really understand why the policy is good.
I don't think the algorithm understands why the policy is good. I think there's this really interesting issue about so we often talk now about, fairness, accountability, and transparency, and interpretability. And I think in some cases we want interpretability, and in some cases I think we want accountability, and we want guarantees. And so this is more about guarantees. This is saying, like, we want to know this is good. And I think the example I like to think about is microwaves. So many of us do not really understand how our microwave works, but almost nobody is worried that their microwave is going to kill them. And this is because when we tell people that they should use microwaves, we don't say 9 out of 10 times a microwave hasn't killed you, which is kind of what we do with machine learning, right? We're like 9 out of 10 times the facial recognition did the right thing. So we often have these sort of probabilistic or data-based guarantees instead of, something that's based on physics or something that we're sure we can verify or we're guaranteed of. And so this is more going towards like accountable and guaranteed reinforcement learning. It's saying, well, it's probabilistic, so it's these bounds only hold with high probability, but it's much stronger than just looking at empirical performance, just looking at averages. I think it depends on the application. I think the level that you need will depend vastly. If it's something like whether I show the right ad to someone, that might be fine. If I'm making a decision that has really high stakes for someone, like chemotherapy decisions, 95 may not be sufficient. And I think one really interesting thing is we don't fully know how people want to make their decisions, what forms of uncertainty we should show to them in order for them to feel like they've gotten the information they need.
Great. Thank you for all the questions. We'll continue in the back room. Let's thank the speaker again. Thank you.
Thanks for having me.